The universe is expanding, not just growing, not just spreading outward from some central explosion, but stretching every point, moving away from every other point, space itself swelling between galaxies like dough rising in an oven. This much we've known for nearly a century. But what scientists discovered in 1998 changed everything we thought we understood about the cosmos. The expansion isn't slowing down as gravity should dictate. It's accelerating. Something is pushing the universe apart, and we have no idea what it is. Close your eyes and imagine standing on the surface of a balloon while someone inflates it. Every dot on that balloon moves away from every other dot, not because the dots are moving through the rubber, but because the rubber itself is expanding. Now imagine that the balloon is accelerating, inflating faster and faster with each passing moment, driven by an invisible force that seems to defy everything we know about physics. This is the universe you inhabit right now, and the force causing this acceleration is one of the deepest mysteries in science. We call it dark energy, but that name is a placeholder, an admission of ignorance dressed in scientific language. Dark because we cannot see it, cannot detect it directly, cannot even confirm it exists, except through its gravitational effects. Energy because it seems to exert pressure, to do work on the fabric of space itself. But what it actually is, where it comes from, why it exists, these questions have no answers. What makes dark energy truly unsettling isn't just that it's unknown, it's that it dominates everything. Current measurements suggest that approximately 68% of all the energy in the universe exists as dark energy. Not atoms, not heat, not even the mysterious dark matter that outweighs all visible matter, but this stranger, more pervasive dark energy that fills every cubic centimeter of space and pushes the cosmos apart. The discovery came from studying distant supernovae, stellar explosions, so bright they can be seen across billions of light years. Type Ia supernova occur when white dwarf stars accumulate matter from companion stars until they reach a critical mass and explode with nearly identical brightness. This uniformity makes them cosmic standard candles. If you know how bright they actually are, you can determine how far away they are by measuring how dim they appear. Two independent teams in the late 1990s measured dozens of these distant supernovae, expecting to find that the universe's expansion was slowing down due to gravity. Instead, they found the opposite. The distant supernovae were dimmer than expected, meaning they were farther away than they should be if expansion were decelerating. The universe wasn't just expanding, it was accelerating. The announcement shocked the physics community. It violated intuition, contradicted expectations, demanded explanations that didn't exist. Gravity is attractive. It should slow expansion, eventually perhaps reversing it into a big crunch where the universe collapses back on itself. but observations showed the opposite occurring. Some repulsive force, some anti-gravity effect, was overwhelming gravitational attraction on cosmic scales. Scientists scrambled for explanations. Perhaps the supernova data was wrong, contaminated by dust that dimmed distant explosions more than expected. Perhaps the universe's geometry was stranger than assumed. Perhaps something about cosmic evolution changed how supernova behaved in the distant past. But further observations confirmed the result. Independent measurements using different techniques, studying the cosmic microwave background, mapping the large-scale structure of galaxies, measuring baryon acoustic oscillations, all pointed to the same conclusion. The expansion is accelerating. This left physics with a profound problem. The equations of general relativity, Einstein's theory of gravity, do permit accelerated expansion, but only if something with negative pressure fills space. Normal matter and energy have positive pressure that push outward on their containers. But dark energy, if it exists, must have negative pressure, pulling inward on space itself, while simultaneously causing space to expand. This seems paradoxical, counterintuitive, almost nonsensical. Einstein's own equations included a term he called the cosmological constant, represented by the Greek letter lambda. He introduced it to make the universe static because he believed, along with most astronomers of his time, that the universe was eternal and unchanging. When Edwin Hubble discovered that galaxies are receding from us, proving the universe expands, Einstein reportedly called the cosmological constant his biggest blunder and removed it from his equations. But the cosmological constant never really went away. It represents a possible energy density of empty space itself, a vacuum energy that remains constant as the universe expands. While matter and radiation dilute as space grows, the same number of particles spread over larger volume vacuum energy doesn't dilute. If space itself has energy, then creating more space creates more energy, and this energy could drive accelerated expansion. The problem is calculating what the vacuum energy should be. Quantum field theory predicts that empty space isn't truly empty, but seethes with it, virtual particles constantly appearing and disappearing, borrowing energy from the vacuum for brief moments. When physicists calculate the energy density these quantum fluctuations should create, they get a number that's approximately 10 to the 120th power larger than observed dark energy density. This is called the cosmological constant problem, and it represents the worst prediction in the history of physics. Theory and observation disagree by 120 orders of magnitude, a discrepancy so enormous it seems to mock our understanding of fundamental physics. Either quantum field theory is profoundly wrong about vacuum energy, or some unknown mechanism cancels out almost all of it, leaving only the tiny residual we observe as dark energy. Some scientists propose that dark energy isn't constant, but changes over time, a possibility called quintessence. The name comes from ancient philosophy's fifth element, beyond earth, water, air, and fire. In cosmology, quintessence refers to a dynamic scalar field similar to the Higgs field that gives particles mass, that evolves as the universe expands. Unlike the cosmological constant, quintessence could vary in strength and even reverse, potentially slowing or reversing cosmic acceleration in the future. Testing whether dark energy is constant or changing requires precise measurements across cosmic time. Scientists study how dark energy's influence has evolved by observing supernovae at different distances, equivalent to looking at different epochs in cosmic history. So far, observations are consistent with a cosmological constant, but uncertainties remain large enough that quintessence can't be ruled out. Other theories propose even more radical possibilities. Perhaps dark energy isn't a substance, but a modification of gravity itself. Einstein's general relativity has been tested extensively within the solar system and with binary pulsars, but cosmic scales are vastly larger. Maybe gravity behaves differently across billions of light years, weakening in a way that mimics dark energy's effects. Modified gravity theories like modified Newtonian dynamics, and more sophisticated alternatives attempt to explain cosmic acceleration without invoking mysterious energy. But these theories face challenges. They must match general relativity's predictions, where it's well tested, while deviating in precisely the right ways to explain dark energy and sometimes dark matter. Most proposed modifications either fail to match observations or introduce new problems more severe than those they solve. Another possibility is that we're misinterpreting observations entirely. Perhaps the universe isn't homogeneous on the largest scales, as cosmologists assume. If we happen to live in a lower density region, surrounded by higher density regions, a cosmic void light traveling to us from distant galaxies would behave differently than standard models predict, potentially mimicking dark energy's effects. This void model faces observational challenges. The cosmic microwave background shows that the universe is extraordinarily uniform on large scales, with density variations of only 1 part in 100,000. Creating a void large enough to explain observations without violating this uniformity is difficult. Moreover, independent measurements like baryon acoustic oscillations confirm acceleration in ways that void models struggle to explain. As you lie here listening, dark energy fills the space around you, between atoms, inside atoms, everywhere. Its density is incredibly tiny, approximately 6 protons worth of energy per cubic meter, but space is vast, and that tiny density adds up. Dark energy's total contribution exceeds all matter and radiation combined. making it the dominant component of cosmic energy budget. Yet we cannot feel it, cannot detect it locally, cannot even confirm it exists through any experiment on Earth. Dark energy's effects appear only on cosmic scales, across millions and billions of light years. Its influence is so subtle that galaxies bound together by gravity don't notice it. Only the vast spaces between galaxy clusters show its accelerating effects. This raises unsettling questions about the nature of space itself. Space, as we experience it, seems like nothing an empty stage where matter and energy perform. But modern physics suggests space is far from empty, that vacuum itself possesses properties and structure that shape everything within it. The quantum vacuum seethes with activity, particle pairs appearing and vanishing, fields fluctuating, energy borrowing and returning in accordance with Heisenberg's uncertainty principle. These aren't mere mathematical abstractions. The Casimir effect demonstrates vacuum fluctuations experimentally. Place two uncharged metal plates very close together in a vacuum, and they attract each other, pushed together by the pressure of quantum fluctuations in the space around them. The region between plates excludes certain wavelengths of virtual particles, creating lower pressure than outside, and the plates are pressed together by this asymmetry. The Casimir force is real, measurable, tiny, but detectable with sensitive instruments. It proves that empty space has structure, that vacuum isn't nothing but a complex medium with properties. If vacuum can exert forces on metal plates, perhaps it can exert forces on space itself, driving cosmic expansion. But here's what troubles physicists. The vacuum energy calculated from quantum field theory should curve space so intensely that the universe couldn't exist as we know it. Either it would have collapsed immediately after the Big Bang, or expanded so rapidly that no structures could form. The fact that we exist, that galaxies exist, that stars and planets exist, suggests vacuum energy is either far smaller than predicted or canceled by some unknown mechanism. This is the cosmological constant problem in sharper focus. It's not just that theory and observation disagree. It's that if theory were correct, we wouldn't be here to notice the disagreement. The universe we inhabit seems impossibly balanced. Vacuum energy precisely tuned to allow structure formation while still causing accelerated expansion. Some scientists invoke the anthropic principle. We observe this particular value because only universes with this value can produce observers. In a multiverse with countless universes having different vacuum energies, only those with values near ours would permit complexity and life. We necessarily find ourselves in one of the rare examples where conditions are right. Others find this explanation unsatisfying, a retreat from genuine understanding into statistical selection effects. Just because anthropic reasoning might be correct doesn't make it satisfying. It converts a deep question about physics into a tautology about observation, explaining nothing about why the multiverse exists or why vacuum energy varies between universes. Alternative approaches seek a dynamical mechanism that sets vacuum energy to its observed value. Perhaps some field evolves over time, relaxing toward a minimum where vacuum energy is small but non-zero. Perhaps quantum gravity effects that we don't yet understand naturally drive vacuum energy toward tiny values. Perhaps the problem lies in how we formulate quantum field theory, and a more complete theory would naturally predict the observed value. None of these ideas have produced testable predictions that distinguish them from competitors. Dark energy remains as mysterious as when it was discovered, a placeholder name for ignorance that dominates the universe's energy budget. Meanwhile, observations continue refining what we know about dark energy's properties. The Planck satellite measured the cosmic microwave background with unprecedented precision, constraining how dark energy affects the universe's expansion history. Large galaxy surveys, like the Dark Energy Survey and the Sloan Digital Sky Survey, map the three-dimensional distribution of galaxies, measuring how dark energy influences cosmic structure formation. These observations provide constraints on the equation of state of dark energy, a parameter called W that describes the ratio of pressure to energy density. For a cosmological constant, W equals exactly -1. For quintessence and other dynamic dark energy, W could differ from -1 and might change over time. Current measurements suggest W is very close to -1, consistent with a cosmological constant, but uncertainties remain. Future missions aim to measure W with even greater precision. The European Space Agency's Euclid satellite, launched in 2023, will map billions of galaxies and measure how cosmic structure evolved over the past 10 billion years. NASA's Nancy Grace Roman Space Telescope, scheduled for the mid-2020s, will conduct even more detailed surveys, measuring dark energy's effects through multiple independent techniques. These missions will determine whether dark energy is truly constant or evolves over time. If W differs significantly from -1, or if it changes across cosmic history, that would rule out the cosmological constant and point toward quintessence or more exotic alternatives. If W remains stubbornly at -1, the cosmological constant becomes harder to avoid, and the fine-tuning problem becomes more acute. Some researchers investigate whether dark energy might be an illusion, an artifact of assuming the universe is homogeneous when it's actually more complex. Perhaps back reaction, the way small-scale structure affects large-scale evolution, creates apparent acceleration without requiring dark energy. Imagine ocean waves. Averaging their motion might suggest the water surface is rising uniformly, when actually it's undulating with peaks and troughs that create a misleading average. Back reaction models face mathematical challenges. General relativity is nonlinear, meaning you can't simply average local geometries to get the global geometry. The universe's large-scale behavior might differ from what you'd predict by averaging local regions. But calculating these effects rigorously is extraordinarily difficult, and most studies suggest back reaction is too small to explain observed acceleration. Still, other theories propose that what we interpret as dark energy is actually a fifth force, an additional fundamental interaction beyond the four we know. This fifth force would be repulsive on cosmic scales, but negligible locally, affecting galaxy cluster separation without influencing solar system dynamics. Detecting such a force would require incredibly sensitive measurements of how gravity behaves across different distance scales. Tests of gravity at various scales have found no evidence of deviations from general relativity. Lunar ranging experiments, which bounce lasers off mirrors left on the moon by Apollo astronauts, confirm Newtonian gravity to extraordinary precision at solar system scales. Binary pulsar timing confirms general relativity at stellar scales. Galaxy rotation curves and gravitational lensing probe galactic scales. Only at the largest scales, tens to hundreds of millions of light years, does dark energy's influence dominate. This scale dependence makes testing difficult. We can't create cosmic scale experiments or observe the universe from outside. We're embedded within the system we're trying to measure, limited to observations from one location at one epoch. Imagine trying to understand ocean currents by sitting at a single point on the sea floor, unable to move, measuring only the water flowing past. That's cosmology's predicament. Despite these limitations, scientists have developed clever techniques to probe dark energy's properties. Baryon acoustic oscillations, the same sound waves that propagated through the early universe before recombination left imprints in how galaxies cluster. These imprints provide a standard ruler, a known physical length that appears different sizes at different distances depending on how the universe has expanded. By measuring baryon acoustic oscillations at multiple redshifts, it's equivalent to multiple epochs in cosmic history, researchers can reconstruct the expansion history and infer dark energy's evolution. The results consistently show acceleration beginning approximately 5 to 6 billion years ago, roughly when dark energy's density became comparable to matter density. This timing isn't coincidental. When the universe was younger and denser, matter dominated the energy budget, and gravity slowed expansion. As the universe expanded, matter diluted while dark energy remained constant, eventually becoming dominant. The transition from deceleration to acceleration occurred when these two energy densities became equal, called the matter-dark energy equality. But why did this transition occur roughly when it did, when conscious observers exist to notice? This is called the cosmic coincidence problem. If dark energy is a cosmological constant, its density was always the same, while matter density was higher in the past and will be lower in the future. The fact that we live at an epoch when the two are comparable differing by only a factor of a few seems suspiciously fortunate. Anthropic reasoning offers one explanation. If dark energy dominated much earlier, structures wouldn't have formed and observers couldn't exist. If it dominates much later, observers would evolve before noticing its effects. We necessarily observe the transition epoch because that's when observers are possible. But again, this explanation feels incomplete, converting mystery into tautology. Quintessence models can alleviate the coincidence problem if the field evolves such that its density naturally tracks matter density for some period before diverging. These tracker models have the field's energy density remain proportional to radiation or matter for cosmic epochs, only recently becoming dominant. But constructing realistic tracker models with natural initial conditions and realistic particle physics remains challenging. As observations eliminate possibilities, dark energy becomes more mysterious rather than less. Each new measurement confirms acceleration, rules out certain models, tightens constraints on parameters, but doesn't bring us closer to understanding what dark energy actually is. The phenomenon becomes even stranger when you consider its implications for the far future. Dark energy, if it continues behaving as observations suggest, will doom the universe to an increasingly cold, dark, and lonely fate. As acceleration continues, galaxy clusters beyond our local group will recede beyond the cosmic horizon, their light redshifted until no photons reach us. The observable universe will shrink, containing only the Milky Way and its gravitationally bound neighbors Andromeda, Triangulum, and a few dozen dwarf galaxies. Eventually, even these neighbors will merge into a single massive galaxy, a cosmic island surrounded by darkness in all directions. The cosmic microwave background will cool until it becomes undetectable. No evidence of the Big Bang will remain visible. Future civilizations in that era would find themselves in a universe that appears static and eternal, unable to discover cosmology as we know it. This future isolation troubles some scientists. It suggests that our current epoch is special, that we live at a unique time when the universe's history is still discoverable. Earlier, no observers existed. Later, critical evidence will have disappeared beyond the horizon. We inhabit a brief window when consciousness can understand cosmic origins. But dark energy might not remain constant. If it's quintessence or some other dynamic field, its strength could change, potentially slowing or even reversing acceleration. Some models predict that dark energy will strengthen over time, leading to scenarios far more dramatic than mere cosmic isolation. The Big Rip is one such scenario. If dark energy strengthens sufficiently, if W becomes more negative than -1, a condition called phantom energy, then acceleration will increase without bound. Eventually, dark energy would overcome not just cosmic gravity, but all binding forces. Galaxy clusters would be torn apart, then galaxies, then solar systems, then planets, then molecules, then atoms. In the final moments before the Big Rip, even space itself would be shredded, atomic nuclei ripped apart, particles separated from their own quantum fields. Current observations don't support phantom energy W, appears consistent with exactly -1, but uncertainties allow for the possibility. If the Big Rip is our future, it lies perhaps 100 billion years away, far beyond any timescale relevant to human concerns, but unsettling nonetheless. Other scenarios involve phase transitions in the dark energy field. If dark energy is a scalar field in a false vacuum state, similar to how inflation might have occurred, it could eventually tunnel to a true vacuum with different properties. This vacuum decay would create a bubble of new vacuum, expanding at the speed of light, destroying everything in its path as the laws of physics themselves changed. We wouldn't see it coming. The bubble wall would approach at light speed, giving no advance warning. One moment the universe as we know it, the next moment gone, replaced by a cosmos with different physical constants, different particle masses, different forces. Life as we know it couldn't exist in the new vacuum. We would be erased faster than neurons can fire. This sounds like science fiction, but the physics is sound. Scalar fields can have multiple vacuum states, and quantum tunneling between them is well established. Whether dark energy is such a field, and whether it exists in a metastable state that could decay, remains unknown. But the possibility exists, and nothing in current physics forbids it. Some physicists calculate that if our vacuum is metastable, it might have a lifetime of billions or trillions of years, far longer than the universe's current age, but finite nonetheless. Others argue that anthropic selection should make us suspicious of fine-tuning. If vacuum decay were too likely, we wouldn't be here to worry about it, so we should expect to find ourselves in a relatively stable vacuum. But these are probabilistic arguments about fundamentally uncertain physics. We don't know enough about dark energy to assess its stability or predict its future evolution. We're making educated guesses based on incomplete theories about a phenomenon we don't understand. Meanwhile, some researchers investigate connections between dark energy and dark matter. These two components dominate the cosmic energy budget, but are usually treated as independent. Dark matter interacts through gravity, clustering into galaxies and galaxy clusters. Dark energy remains uniformly distributed, pushing space apart. But perhaps they're related, two aspects of a single underlying phenomenon. Unified dark matter models propose scalar fields, or modified gravity theories, that produce both dark matter-like clustering and dark energy-like acceleration. These models face significant challenges matching observations, because dark matter and dark energy have such different properties and behaviors. Dark matter was dominant early, dark energy only recently. Dark matter clusters, dark energy doesn't. Unifying them requires delicate balancing of parameters. Other connections might be more subtle. Perhaps dark matter interacts weakly with dark energy, or perhaps dark energy's properties depend on local dark matter density. These interactions could leave signatures in cosmic structure formation or in the distribution of galaxy clusters. Observations constrain these possibilities, but haven't ruled them out entirely. The Large Hadron Collider searches for dark matter particles, attempting to create them in high-energy collisions. So far, no convincing candidates have appeared, though hints and anomalies continue emerging and fading. Direct detection experiments deep underground wait for dark matter particles from the galaxy to scatter off atomic nuclei. Again, no definitive signals, only tantalizing hints that vanish under scrutiny. If dark matter and dark energy are connected, discoveries in particle physics might illuminate cosmology and vice versa. A dark matter detection could constrain dark energy models. Precision measurements of dark energy's evolution could predict dark matter properties. The two mysteries might be facets of a single, deeper mystery. But progress requires better observations and deeper theory. Current measurements of dark energy are precise, but not precise enough to distinguish many competing models. Next-generation experiments aim to achieve the necessary precision, measuring dark energy's equation of state to a few percent accuracy across cosmic history. These experiments use multiple complementary techniques. Type Ia supernova remain crucial standard candles, with surveys discovering thousands of examples across cosmic time. Baryon acoustic oscillations provide standard rulers, with galaxy surveys mapping their distribution in 3 dimensions. Weak gravitational lensing measures how mass, both dark and luminous, distorts background galaxy images, probing dark energy's influence on structure formation. Combining these techniques reduces systematic uncertainties. Each method has different sources of error, different assumptions, different sensitivities. Agreement between methods provides confidence that results reflect reality rather than hidden biases in one technique. The Dark Energy Spectroscopic Instrument, DESI, which began operations in 2021, will measure redshifts for tens of millions of galaxies, mapping cosmic structure with unprecedented detail. By tracking how baryon acoustic oscillations evolved over the past 11 billion years, DESI will constrain dark energy's properties across most of cosmic history. The Vera C. Rubin Observatory, beginning operations in the mid-2020s, will conduct the legacy survey of space and time, photographing the entire visible sky every few nights for 10 years. This survey will discover millions of Type Ia supernova, measure weak gravitational lensing across billions of galaxies, and track how cosmic structure evolves over time. Together, these and other experiments will determine whether dark energy is a cosmological constant or something more complex. They'll measure whether W equals -1 to high precision, or whether deviations emerge that point toward quintessence, modified gravity, or more exotic possibilities. But even definitive measurements might not provide understanding. Suppose we confirm that W equals exactly -1 to 1% precision. That would rule out many quintessence models and support the cosmological constant interpretation, but it wouldn't explain why the cosmological constant has its observed value. The fine-tuning problem would remain, perhaps intensified by the certainty that the value is exactly what it appears to be. This is where physics stands regarding dark energy, surrounded by observations that confirm its existence, armed with theories that predict its properties, yet profoundly ignorant about its fundamental nature. We know what it does: drives accelerated expansion. We know how much exists about 68% of cosmic energy density. We know when it became dominant about 5 billion years ago. But we don't know what it is, where it comes from, or why it exists. And the stakes couldn't be higher. The mystery of dark energy extends beyond academic curiosity. It determines the ultimate fate of everything: galaxies, stars, planets, life. The universe's future depends entirely on dark energy's nature and evolution. If it's a cosmological constant, the universe will expand forever, accelerating into cold, dark isolation. If it's quintessence that decays, expansion might slow or reverse. If it's phantom energy, the big rip awaits. If vacuum decay is possible, erasure could come at any moment. These aren't distant, abstract possibilities. They're the cosmic context within which all other questions exist. The future of intelligence, of consciousness, of information itself, depends on understanding dark energy. And right now, we don't. Some researchers approach the problem through quantum gravity, attempting to build theories that merge general relativity with quantum mechanics. String theory proposes that particles are vibrating strings in a 10 or 11-dimensional space. These extra dimensions are compactified, rolled up so small we can't detect them, but their geometry determines the properties of our four-dimensional universe, including vacuum energy. String theory predicts that many different compactifications are possible, each producing different physics, different particle masses, different forces. This landscape of possible universes might number 10 to the 500th power or more, an incomprehensibly vast collection of potential realities. Our universe would be just one point in this landscape, with our observed vacuum energy corresponding to one particular compactification geometry. But this explanation recreates the anthropic problem at a new level. If the landscape exists, and all compactifications are realized somewhere in a multiverse, then explaining our particular vacuum energy reduces to selection effects. We exist in a universe where vacuum energy permits structure formation. The vast majority of landscape points would have vacuum energies too large or too small for complexity. But we necessarily find ourselves in one of the rare exceptions. Some physicists find this satisfying. It converts an apparent fine-tuning into a statistical inevitability. Others find it a retreat from explanation, replacing a specific question with an untestable multiverse populated by unobservable universes. The debate continues, highlighting tensions between mathematical elegance and empirical verification. Loop quantum gravity offers an alternative approach to quantum gravity, proposing that space itself is made of discrete loops at the Planck scale. This discreteness might affect how vacuum energy is calculated, potentially resolving the discrepancy between quantum field theory and observation. But loop quantum gravity hasn't yet produced definitive predictions for dark energy's value. Other theories propose that space has more than 3 dimensions at large scales, not just small ones. In brain cosmology, our universe might be a 3-dimensional membrane floating in a higher dimensional bulk space. Gravity could leak into the bulk, weakening at cosmic scales and mimicking dark energy's effects. Nearby brains might influence our universe through gravitational effects, creating apparent acceleration without requiring energy. These ideas make testable predictions. If gravity weakens at cosmic scales due to extra dimensions, this would affect gravitational wave propagation. The LIGO and Virgo detectors, which discovered gravitational waves from merging black holes and neutron stars, can test whether gravity behaves as general relativity predicts. So far, observations confirm standard gravity, placing constraints on extra-dimensional models. Another approach investigates whether dark energy might be related to information or entropy. Black holes have entropy proportional to their surface area, suggesting deep connections between gravity, quantum mechanics, and information. Perhaps the universe's accelerated expansion is driven by entropic forces, by the tendency of systems to evolve toward maximum entropy. Entropic gravity proposals face challenges matching all observations, but the idea that gravity might be emergent rather than fundamental has gained serious attention. If space and gravity emerge from quantum entanglement or other information theoretic principles, Dark energy might be a natural consequence of how the universe's information content evolves. Meanwhile, some physicists question whether dark energy is the right framework at all. Perhaps we're misinterpreting observations, and the universe's expansion history is stranger than we think. The distance ladder, the series of methods used to measure cosmic distances, relies on assumptions that might be wrong. If systematic errors exist in how we calibrate standard candles or standard rulers, apparent acceleration could be an artifact. Tests of the distance ladder use multiple independent methods. Kiffide variable stars, whose pulsation periods correlate with their intrinsic brightness, calibrate type Ia supernova distances. Red giant stars provide another calibration. Gravitational lensing time delays offer yet another. When these methods agree, it builds confidence that distances are correct. Currently, different methods show some tension. They don't agree perfectly, but all support cosmic acceleration. The Hubble tension is one such discrepancy. Measurements of the Hubble constant, the current expansion rate, differ depending on method. Local measurements using the distance ladder give higher values than measurements from the cosmic microwave background. This tension might indicate systematic errors, or it might point to new physics, perhaps evolution in dark energy, or unexpected features in the early universe. Resolving the Hubble tension is a priority for observational cosmology. If systematic errors explain the discrepancy, identifying and correcting them will improve confidence in other measurements. If new physics is responsible, discovering what it is could revolutionize our understanding of dark energy and cosmic evolution. As these investigations continue, dark energy's mystery deepens rather than resolves. Every new observation confirms its existence while raising new questions. Every theoretical proposal either fails to match data or introduces new fine-tuning. The phenomenon seems specifically designed to frustrate understanding, to resist every attempt at explanation. Some scientists wonder whether this resistance is telling us something fundamental. Perhaps dark energy is a clue that our current framework's general relativity, quantum field theory, the standard model of particle physics, are incomplete in crucial ways. Perhaps the universe is trying to teach us something, and we're not listening properly. The history of physics is filled with mysteries that seemed intractable until conceptual breakthroughs reframed the questions. Newton couldn't explain why gravity exists, only how it behaves. But Einstein reinterpreted gravity as space-time curvature. Classical physics couldn't explain atomic stability or black body radiation until quantum mechanics provided new frameworks. Perhaps dark energy awaits similar conceptual revolution. What might that revolution look like? Perhaps time itself is an emergent property rather than fundamental, and dark energy reflects how emergent time behaves at cosmic scales. Perhaps space has quantum properties we haven't recognized, and dark energy is a macroscopic quantum effect. Perhaps the universe is a quantum computer, and dark energy represents computational resource allocation across cosmic scales. These ideas sound speculative, even absurd, but so did quantum mechanics to early 20th century physicists. The mathematics of wave-particle duality, quantum entanglement, and superposition seem to violate common sense, yet experiments confirmed every prediction. Perhaps dark energy will require equally radical reconceptions of reality. Or perhaps the answer is simpler than we think, hidden in some overlooked detail of known physics. Perhaps a subtle error in how we apply general relativity to cosmology creates apparent dark energy where none exists. Perhaps the universe's geometry is more complex than we assume, creating optical illusions that mimic acceleration. Testing these possibilities requires observations of unprecedented precision and theoretical work of exceptional creativity. Both are ongoing, with thousands of researchers worldwide dedicated to understanding dark energy. Conferences convene, papers publish, telescopes observe, and gradually the constraints tighten. The possibilities narrow. The truth becomes clearer, even if that truth is that we don't yet have the conceptual tools to understand what we're seeing. As you rest here, dark energy fills the space around you, between these words, within your thoughts. Its effects are too subtle to feel, too weak to measure locally, too slow to notice, but over cosmic time and distance, it dominates everything. The space you occupy will someday expand beyond reach of any civilization, carried by dark energy into eternal isolation. Unless dark energy changes, unless our understanding is wrong, unless the universe has surprises still waiting. In the end, dark energy confronts us with the limits of human knowledge. We've constructed elaborate theories, built magnificent instruments, gathered vast datasets, yet the universe's dominant energy component remains mysterious. This should humble us, remind us how much we don't know, how far we are from complete understanding. But it should also inspire us. A century ago, we didn't know galaxies existed beyond the Milky Way. We didn't know the universe was expanding. We didn't know about the Big Bang, cosmic microwave background, dark matter, or countless other discoveries. Each generation of scientists has pushed further into the unknown, revealing truths previous generations couldn't imagine. Dark energy is our generation's great mystery, the phenomenon that defines contemporary cosmology. Future historians might look back on our era as the epoch when humanity first glimpsed dark energy, just as we look back on Hubble's discovery of cosmic expansion or Galileo's first telescopic observations. We stand at the beginning of understanding, not the end. The next decades will bring remarkable observations. The James Webb Space Telescope, already returning stunning images of the early universe, will observe how galaxies formed and evolved when dark energy was just becoming dominant. LIGO, Virgo, and future gravitational wave detectors will test whether gravity behaves as general relativity predicts across cosmic scales. Particle accelerators might discover new fields or particles that illuminate dark energy's nature. Perhaps the breakthrough will come from unexpected direction and accidental discovery, a theoretical insight, a connection between previously separate fields of physics. Perhaps a young student reading this right now will be the one to solve the mystery, bringing together observations and mathematics in ways no one has tried before. Or perhaps dark energy will remain mysterious for centuries, a known unknown that future scientists chip away at slowly, measurement by measurement, theory by theory, until someday the truth emerges. Science doesn't promise quick answers. Only that persistent questioning eventually yields understanding. What we do know is that dark energy is real. Whatever it is, whatever it's called, something is pushing the universe apart. The observations are too consistent, too reproducible, too well confirmed by independent methods to be mistake or coincidence. Dark energy exists, and understanding it is one of the great challenges facing physics. Some scientists fear that dark energy might be fundamentally unknowable, that we've reached the limits of what observation and experiment can reveal. Perhaps we'll never directly detect dark energy, never build instruments sensitive enough to measure it locally, never probe the energy scales where it originates. Perhaps we'll be forever limited to inference and indirect observation, watching its effects on cosmic expansion, while never understanding its nature. But this fear might be unfounded. The history of science teaches that mysteries yield to persistent investigation. Nature doesn't deliberately hide its secrets. It simply operates according to principles we must work to discover. Dark energy seems mysterious now, but so did electromagnetism before Maxwell, radioactivity before Becquerel, nuclear fusion before Beatty. Each mystery, once solved, reveals deeper mysteries. Understanding dark energy won't end physics. It will open new questions, new domains of investigation, new puzzles to solve. Perhaps dark energy connects to quantum gravity, providing clues about Planck scale physics. Perhaps it relates to the multiverse, confirming that other universes exist. Perhaps it reveals entirely new forces or particles. The quest to understand dark energy drives technological development. Better telescopes, more sensitive detectors, faster computers, more sophisticated analysis, all flow from the attempt to measure cosmic acceleration precisely. These technologies find applications beyond cosmology, benefiting medicine, communications, engineering. Basic research has always produced practical benefits, even when that wasn't the goal. More importantly, studying dark energy expands human consciousness. Every child who looks at the night sky and wonders what's out there, every student who studies cosmology, every citizen who reads about scientific discoveries, all participate in humanity's quest to understand the cosmos. We are the universe becoming aware of itself, matter arranged to contemplate matter, consciousness emerging from unconsciousness. Dark energy reminds us that the universe is stranger than we imagine, that reality doesn't conform to intuition or common sense. It operates according to mathematical principles that must be discovered through observation and reasoning, not assumed based on everyday experience. This lesson applies beyond physics. It's a reminder that truth is discovered, not invented, and that our preconceptions must yield to evidence. As accelerated expansion continues, as galaxy clusters recede beyond the cosmic horizon, as the observable universe shrinks, we exist in a privileged moment. We can still see the cosmic microwave background, still detect baryon acoustic oscillations, still measure dark energy's effects across cosmic history. Future civilizations won't have these opportunities. The evidence will have disappeared beyond the horizon. This makes our investigations urgent, not in a practical sense, but in an intellectual one. We have a brief window, cosmically speaking, to figure out what dark energy is before the evidence becomes inaccessible. This is our moment to understand, our chance to answer one of the universe's deepest questions. Perhaps the answer will come in your lifetime. Perhaps you'll wake one morning to headlines announcing that dark energy has been explained, that some brilliant experiment or theoretical insight has revealed its nature. Or perhaps the mystery will persist, waiting for future generations to solve. Either way, the search itself matters. The attempt to understand, the refusal to accept ignorance, the determination to keep questioning, these define the scientific endeavor. Dark energy doesn't frighten scientists because it's unknown. It excites them, challenges them, motivates them to build better instruments and develop better theories. As you drift towards sleep, consider that you're floating in space filled with mysterious energy, that the ground beneath you is being carried by cosmic acceleration toward an uncertain future, that the very fabric of reality contains forces we don't understand. This should be comforting, not frightening. It means the universe still holds wonders to discover, that the story of science isn't over, that mystery and possibility remain. The strange forces guiding our expanding universe aren't just physics problems. They're invitations to wonder, to question, to seek understanding. They remind us that we don't have all the answers, that reality is deeper and richer than our theories capture, that the cosmos still has secrets waiting to be revealed. Before you drift into sleep, remember, mystery is never truly lost, only waiting to be found. The universe whispers its secrets through starlight and mathematics, through observations and equations, through the persistent questioning of those who refuse to accept "we don't know" as a final answer. If you enjoyed this journey through cosmic mysteries, subscribe for more relaxing explorations of the unknown, and let your curiosity guide you deeper into the questions that connect us to the very fabric of existence. The universe holds secrets still, written in the expansion of space itself, in the acceleration we don't understand, in the dark energy that fills everything and explains nothing. Sweet dreams, cosmic explorer, and may your rest be as peaceful as space itself, expanding quietly into the mystery of tomorrow.